are the most important elementary reactions, we would have to do or could do some kind of atom flux analysis, and that is where is the majority of the atoms going through, and these are the most important reactions. And then, for instance, for a larger system like if we want to burn kerosene, we may have 2,000, 3,000 individual elementary reactions. We need to identify the most important one, that we are able to reduce the mechanism to a system which we can handle in the CFD program. So this would be a reduced chemical mechanism. And one way to generate this reduced mechanism would be some atom flux analysis. Okay. So we are at the number of atoms of element of a certain element in a molecule, and then we have the total number of certain atom in the system. This is also if we aim at a equation of conservation of atoms in the system, what comes in, what comes out. And we even may have an element or an atom mass function. So the number of atoms, what we have at a certain of a mass of a certain element divided by the total mass in the system. So we see we have the elements, the mass, and the x would be the mole fractions. So these are Z, Y, X, the key things which characterize the concentration of atoms, of species, or moles, or mass in the system. And per definition, if we sum all them up, we have one. Now we could sort of also specify the number of moles per unit volume. That we have, not the entire system, but we define, for instance, 1 cubic centimeter or 1 cubic meter, that we have an idea that can link that also to some kind of density argument, what we quite often have to take into account if we talk with continuity equation, we have also the density in the system. So density is important, and that's the reason why we use something which makes use of a mole of a certain volume. Now what we have then a partial molar density and the density, overall density of the system. This is important for those who know fluid mechanics. Typically we have the system of Reynolds averaging. You know that if we have a turbulent flow, we have some fluctuations, and in principle, Reynolds come up with the idea that any type of fluctuating velocity component can be subdivided into an average, which is in principle, or the instantaneous velocity would be an average plus the fluctuation. Now, this holds for if you don't have large density fluctuation. In combustion process where we have locally sufficient heat release, density is not constant. So on a very small scale, not constant. And that's the reason that we have to do, instead of that Reynolds averaging, some Favre averaging, where we take the density into account in order to fulfill and have a successful formulation of the continuity equation. So that's one of the reasons why we take something like molar partial molar density in order to make sure that we have an idea about the local density or the local concentration of a species in the system. Now, if we come to the process of what is an elementary reaction, I already mentioned that we have even for a very simple combustion process, what we have here, hydrogen, typically it's formulated 2H2 plus O2 gives H2 plus O2H. So, and that would be just two of the elementary reactions. I already mentioned that we have maybe, I think the most detailed mechanism formulates 17, some use 19 individual reactions for that simple hydrogen-oxygen reaction. That star pops up quite often, which is indicating that we have a radical. So a radical is something what we need to generate in order to get a chemical reaction going. And typically we generate radicals by collision of molecules. Collision, I don't like the word because that looks like, or it sounds like molecules are colliding and touching. That's it. We would have to have some hadron collider like CERN or something, but with very, very high energies that they're actually moving. What we are doing instead in chemistry, that we have molecules, gaseous molecules moving, and sometimes they are approaching another, that they feel the electrochemical interaction potential in one another, which slightly changes their own constitution. And if the energy is sufficiently high, which is overcoming the activation energy, we may be able to generate what we call a radical. Radical, the name calls it already said this is something which is ready to initiate the chemical reaction. So whenever we talk about combustion or any type of chemical reaction, the first thing is radical generation. That's essential. We can do that, as I mentioned, by collision. We could also use some kind of laser, meaning that we have some photon in a wavelength which the molecule is able to absorb. That we lift an electron in its potential, we add potential energy to the electron, and that could be sufficient that it's basically we shoot that out of the formation, and then we have a free electron in a radical generated. So this would be another way that we have some laser-induced chemical reaction initiation. But quite often it's just that we have it at sufficient high temperatures that the transversational energy is sufficiently high that a collision is generated by radical. Not each collision is successful. And that would basically be what is in principle shown in this pre-exponential factor. This is just a very simple way of putting it. In principle, it shows that the sort of success frequency, so the frequency, how many collisions do we need in order to have one radical? So that's in that pre-exponential factor. This one is also slightly energy dependent. It depends also on the molecule itself. For instance, if we have some kind of very symmetric molecule like methane, where we have in the center carbon atom and then 4 hydrogen atoms, so it's very symmetric, and this makes it also very stable. If we have some kind of asymmetric molecule where we have already some kind of charge distribution, like the water molecule, that we have on one hand, we have that 100% degree between the center oxygen atom and the hydrogen atom, so there is a slightly positive charge in one area and a slightly negative charge in the other area. If this molecule is basically approaching another molecule, it's easier for them to generate the sort of a successful collision that is able to generate the radical. What we in principle have there would be the activation energy, meaning how much energy we need to put into the system that we are able to generate that radical. So that's a sort of reaction rate. And of course, that's temperature dependent. That's because we are in principle relying on the translation of energy, meaning how fast the molecule is moving. And that gives us the energy, which is basically providing sort of having a potential interaction with another molecule. What is I think is also interesting to know is that we have those arrows. These arrows are an indicator that reactions are able possibly both ways. Meaning, if we are in chemical equilibrium, meaning the production of species is basically negligible, but the number of reactions going back and forth is very, very high. But there is no net production of any species. So equilibrium means no net production, but since typically equilibrium is established at very high temperatures, so any kind of sort of collision between high temperature species or molecules or particles is very high. So there is some high reaction rate, but no net production. So that gives you an idea about if we have a simple molecule like methane, CH4, and we have that reacting with oxygen. So we know that we need to generate some kind of no, this is N-hexane. So yes, it's N-hexane. So this would be a classical molecule what people are using if they model aero engine combustion. So they use, instead of having experiments or modeling kerosene, which is a mixture of maybe hundreds of different kinds of species, they say we just deal with N-hexane, and this is complicated enough. And what I was trying to show you is here that in order to follow the different kind of species, we try to find out what is the most important pathway. And by analyzing the reaction path, we would in principle have an idea or some hint where are we able to sort of influence the reaction and have an impact on the final output. So for instance, if we say, no, we have this one would be an important molecule, but this is leading to a path to generate a species which we don't like because it's an emission which you are not allowed to have. We try to either modify this reaction path by lowering the temperature or increasing the temperature or adding some species that we basically follow this way and end up in a different kind of reaction. So a detailed analysis of the individual reaction of elementary reaction helps us to find a way from the control of the combustion process by locally adding or changing the conditions for the chemical reaction to get favorable conditions. For instance, in aero engines, some people of you may know that we have this kind of, initially we burn fuel rich in order to have the ignition, the flame, to avoid flame out. But fuel rich is something what we do not want, because that would increase the fuel consumption. So at the end, we want to operate lean. So air rich, meaning we have to go from fuel rich to lean. And that means we would have to go through the stoichiometric mixture, and stoichiometric means very high temperatures. Very high temperatures mean that we have favorable conditions for anaerobic production. And we can avoid that if we have that kind of switch from rich to lean very fast, because our analysis of the elementary reaction tells us that the formation of nitrous oxide is a reaction which takes long. So if we make that shift from fuel rich to lean fast, then we avoid the NOx formation for a substantial amount. And if you look into the other engine, they call it a rich, quick quench. So meaning that we quench, that we try to go very fast to the lean reaction and inject a large amount of cold air that we lower the temperature and go fuel rich in a very fast way. In order to avoid a certain reaction path, it would end up into a large amount of NOx. So the main message is it makes sense to analyze in detail the elementary reaction because they may help us in order to improve the combustion process in a way that we get favorable output. So, having talked about the elementary reactions, they are very complicated, but in order to sort of get maybe a better idea, and some of the combustion processes we are only interested in, this is what we throw in. We need a certain amount of heat release, which is generating the power to drive a compressor. Now that would be an aero engine or the rocket engine, basically it would be the same. That we need the working fluid for the turbo machine. Here we are only interested in how much power do we need to generate in order to do that. And for this, we don't need the typically the elementary reaction. It would be sufficient to just take the global reaction because here we know this is the amount of fuel, this is the amount of oxygen we need in order to generate the driving gas, which is compatible with the condition in terms of temperature and mixture of the turbo pump, and that's it. So that was one way to put it into a global reaction. So what we get is what is the input, for instance, any type of hydrocarbon fuel with oxygen, we get a certain carbon dioxide and water. Obviously, this is not telling us the total story because we have byproducts like NOx, air, or even some kind of unburned propellants such as CO. But that would be the global reaction in order to get an idea about what would be the necessary amount of input of fuel in order to generate a certain amount of power. What you find in the literature is this stoichiometric coefficient. So if it's the educts, so we have 1 prime, products are 2 prime. If we look into methane oxygen combustion, so we have methane would be 1, oxygen we need 2 in order to be able to generate the carbon dioxide and the water. So what we would have in order to write down the proper equation, we have to make sure that the number of atoms what we have on the educt side, on the reactant side, is matching the number of atoms what we have in the product side. So these kind of coefficients are to be determined by the number of moles what we need in order to be able to generate the product. So we know methane and oxygen is giving us carbon dioxide and water, and then we see water would be H2O, CO2, so we need 2 oxygen molecules in order to have a balanced equation. So the big advantage is that it shows us the amount of each substance what is in the system. So we can write down here moles, or we can say we can have the molar weight, that we get an idea about the mass per mole, what is involved. So we could use this equation in order to get an idea how much kilogram of oxygen and methane we need and what is the output of carbon. What does also not involve is any type of residence time or time argument, how long does this reaction take? So this is not in the system, and sometimes it's an important, in particular if we do rocket engine, because in the center of the combustion chamber we normally have 3,500 Kelvin, independent if it's hydrogen, oxygen, or even in methane or any type of hydrocarbon, it's 3,400, 3,500 kilograms, depending on the pressure and mixture ratio. So in the boundary layer, we need to cool our combustion chamber, and since we use copper in a rocket engine, we are not able to go to temperatures higher than 900 Kelvin, meaning that in the boundary layer, the gas will be cooled down to 900 Kelvin. And if we look now in reaction times, we will find out that at this low temperatures, some hydrocarbon reactions are not able to reach chemical equilibrium during the residence times. If we think in computation, we sit there in the boundary layer, have our computation itself. The residence time, since the flow velocity is typically high, still in the boundary layer. And it could be that during the residence time of our gases in the computation itself, they don't reach chemical equilibrium, meaning we have to take into account finite rate chemistry in order to find out what is the actual composition. If we would assume chemical equilibrium, which some of the combustion models which are in the literature, like most of the flamelet model, they assume local chemical equilibrium. This is good or sufficient for air engines because the material which is used there is some high temperature steel, typically 1200, 1400 K. There, right, we could use chemical equilibrium. But not in a rocket engine. Here we have to use finite rate chemistry in the boundary layer. And that's important. So we have to think of what kind of combustion model we are using, also chemistry model we are using, depending on the application. So there is no one size fits all. It doesn't work for t-shirts and definitely not for combustion model. Chemistry, I think. So, as I said, we have, for instance, we have a molar reaction. So this basically the stoichiometric coefficient gives us the number of moles what we need. So we have 2 moles of hydrogen, 1 mole of oxygen gives us 2 moles of water. Meaning, you see, this is an example where the number of moles what we have in the system is not concerned. Yeah. So we have 4 grams. So 4 times 4 grams of hydrogen, 32 grams of oxygen gives 36 grams of water, steam, right? So that's the, as I said, that's the advantage of the global reaction, that we can easily deduce the number of moles as well as the mass, which is important. So we can easily say, in order to be able to generate this amount of heat we need, meaning the driving power which is available, we throw in a certain amount of fuel and burn it with a certain amount of oxygen. So typically we could basically count what is the number of atoms in the carbon, the number of hydrogen in the fuel, as well as the number of oxygen. So sometimes we may have oxygen in the fuel. This could be burning alcohol. So one of the early rocket propellants, compound rocket, the early compound rocket, the V2 rockets, meaning the A4 engine was burning oxygen and alcohol. So there was already an oxygen molecule inside the fuel, and which is something which we have to take into account. So we could do a balance. If you recall, I mentioned that we need to balance the atoms. What goes out in has to go out in terms of atoms in a global reaction. Now, you quite often may found, I already mentioned that stoichiometry is in principle a sort of mixture of oxidizer and fuel where both of the molecules are consumed, meaning we have a certain amount of products of reactants which we throw into the system. All of them are consumed and converted into product. So this would be called a stoichiometric mixture. So for instance, for methane oxygen combustion, we would have to have a stoichiometric mixture of four times the amount of oxygen we need in order to burn the 1 gram of methane. We need 4 grams of oxygen, or 1 mole of methane we need 4 moles of oxygen. So this would be stoichiometric mixture. This holds for most of the combustion. However, if we go in terms of, if we go to very high pressure, then Mother Nature kicks in and says, okay, in very high temperature, we are not following this global reaction scheme anymore, because at very high temperature, we are starting to decompose the product water into hydrogen, oxygen, radicals, even generating electrons because of the very high temperature and very high energy. And then this equation doesn't hold anymore, but it gives us an idea at normal conditions in terms of just, let's say, 10, 20 bars, and the conditions what we have in a narrow engine, 2500, 2800 Kelvin, it's still okay. In rocket engines, things are quite often a little bit different because of, if you think of the Raptor engine of SpaceX, we have 300 particles. So this is a different story. Now, there is, since as I already mentioned, that we have not much which is constant in a chemical reaction, people come up with the idea which is called a mixture fraction. That the picture, what is behind, that we have an oncoming flow of separated, let's say by plates, so a mass of oxidizer in the unburned condition and the mass of fuel in the unburned condition. Now we go to a certain condition where we have sufficient condition to initiate the chemical reaction, and then we start what we call here a sort of mixing layer, and then we have a reaction, chemical reaction, and the reaction is spreading. So the mixture fraction, it's defined that it is conserved. So we have molecules are not constant, but the mixture fraction is something which is constant. So we have the stoichiometric condition of fuel, of the mass fraction of the fuel, minus the stoichiometric condition of the oxidizer, plus, so this would be the oncoming, the O2 means this is basically at the other side of the reaction. So mass fraction O2 would mean, I think this is missing in the side, that we have after the chemical reaction. So we try to relate incoming to outgoing, and then have a definition of the mass fractions of fuel to minus the oxidizer, basically the remaining of the oxidizer. And here we have mass fraction of fuel incoming to mass fraction of oxidizer, which is leaving. So that's how we define the mixture fraction, and wherever we are in a system, that gives us the local mixing condition, independent of chemical reaction or no. If we are one side of the definition, if we are in the fuel, then the mixture fraction is 1. And if we are in the oxidizer, the mixture fraction is 0. And wherever we are inside our combustion chamber, we can go at each different position. We locally are able to define a mixture fraction. Now, since we know, even with our combustion process, with the simulation, at each computational cell, we have the concentration of the species. And based on the concentration of the mass fraction of the species, we can define the mixture fraction. It's easier because instead of having those 4, we just have 1. And that helps us to define locally what is the composition, what is the local composition over the entire computational state, from the entire combustion chamber. That's in principle the strength of the mixture fraction, because it's in principle conserved scalar, and you can easily find, for instance, where we have a mixture fraction, which is the stoichiometric mixture fraction. Here we can say this is where the combustion really takes place, at the stoichiometric mixture fraction. So we look at the mixture fraction, we define where we have stoichiometric mixture fraction, and here it's the most likeliest place where a chemical reaction takes place, because here we have locally the highest possible temperature in the system. And a large amount of models, what we have in combustion, are basically trying to define where is the position of the stoichiometric mixture fraction. And this would mean that this is the position where the flame is sitting. And then we can say in a non-premix condition, or even in the premix condition, we have cold flow coming from one side, and if we have stoichiometric mixture fraction, so this is the flame, and on the other side of the flame, it's product. So a large amount of combustion models work that way, that finding the stoichiometric mixture fraction gives you immediately a position where the flame is. And since I already mentioned, if you recall, that we have in a large number of combustion processes in applications, we have temperatures where we can assume temperatures are sufficiently high that we reach chemical equilibrium, and then meaning that the reaction is very fast, meaning the flame is very thin, and that's basically something like a shock wave, similar like a shock wave. And then we can say there's one position it's cold and the other position is hot and it's burning. That makes it simpler also in model. In reality, it's like usual, life is a little bit more complex, but the early models were basically assuming the flame is basically a sheet with infinite thickness. And then you have unburned and burned stuff, and nothing in between. Only more sophisticated say, no, we need some sort of a certain time where we need, when we are cold, we need some kind of heat conduction to heat up the cold reactants. That we reach the auto-ignition temperature, then we may have some turbulence, which helps us mixing. This is sort of, and then we get a sort of finite length flame thickness. And then the more sophisticated models now say we need to have, in order to be really predictive, within the flame thickness, maybe 2 or 3 or 5 computational cells. What when we do some direct numerical simulation about that, then we try to have maybe 5 or 6 computational cells within such. not necessary for every application, but it helps in order to get inside what is going on. For instance, one of the results what we were achieving is that we found out that what normally is not in the textbooks, people normally claim combustion as a result is damping turbulence. The reason is we raise the temperature due to the heat release, and raising the temperature is also increasing viscosity, and increased viscosity is in principle damping the turbulence. So a large number of early combustion models say, okay, temperature increase, there is no turbulence generated by chemical reaction, turbulence is damped by chemical reaction. Now, if we look into resolving the flame sheet, the flame thickness, we see that in the beginning of the cold side of the flame, due to the local heat release, we have a local expansion, and then we are generating on a certain length scale the turbulence. Not on a large scale, but on a smaller scale, the scale of, let's say, the small eddy, we are generating turbulence. And that's, for instance, also violating from what we know, the Kolmogorov hypothesis, that we have a certain decay of turbulence. This is not the case in most of the combustion processes. Yeah. So we have a violation of that Kolmogorov hypothesis due to the fact that if we look in detail, we see that there might be turbulence generation due to reaction. Later on, if the temperature is high enough, then viscosity is overcoming, and then we get better. But you know, that's something which is not all the combustion models. I'm not quite sure if you went that way. Just to keep it in mind that I'm not a combustion modeler. Yeah, I don't believe in models. They are per definition wrong because it's a model. But we need to use those tools, but we have to find out, and that's one of the reasons why we do this, in order to sort of provide you with some kind of knowledge and experience what can go wrong if you do some models, and in order to judge the result. Is it useful? Does it make sense? That you are become a sort of experienced user of those CFD tools. So, as I just mentioned, that's the stoichiometric mixture ratio. You could use this. What people normally use is some kind of mathematical tool, such as where you follow. For instance, if you have the density ratio between a liquid and a gas, again, you could basically define something like the mixture fraction, like the density formulation, and then you follow a two-phase law. That's always the development. If you look into atomization of a jet or a ligament into smaller droplets, that you try to follow the evolution of that phase change boundary. And here we follow the mixture fraction in order to identify where the flame position is. So that's in principle the methane hydrocarbon fuel. So in order to make it simple, we have the stoichiometric coefficient of the fuel, the stoichiometric coefficient of the oxidizer, and then simple just the products. So we recall set in that original we have X, the mole fraction, capital X mole fraction, capital Y mass fraction, capital Z the element mass fraction. And what is done there is to get basically a sort of coupling function with that beta, where we try to combine the element mass fraction of the carbon atom, of the hydrogen atom, and the oxygen atom. And there was some guy called Gilder. He was one of the earlier sort of developers of combustion models. Uh, 30 or 40 years back, or even longer. Yeah. He, in principle, came up with this kind of definition of the mixture fraction with that normalization and the coupling function what we have in the system. Now, what might be for air engines or rocket engines, we don't know about equivalent ratio. So that takes into account the number of nitrogen atoms what we have in air. In rocket engine, we talk about mass fraction. So the amount of oxidizer what we need in order to, let's say, the local mixture, the overall mixture of oxidizer and fuel. And since we offer a fuel rich, typically we are smaller than the stoichiometric mix. So we can relate the mixture fraction to the equivalence ratio. This is something important for aero engine combustion process. The rocket engine, as I said, we don't do that. We have the mass fraction. We don't use nitrogen. We try to burn, because nitrogen would be a dilutant with a very poor expansion coefficient. So the efficiency if we would use nitrogen doesn't make sense. Combustion temperatures would be small, and NOx formation will also increase the molecular weight. And since we are riding on the exhaust jets, the molecular weight of the exhaust jet is basically defining how fast the exit velocity, the higher the molecular weight of the exhaust gas, the lower the jet velocity is. And riding on the jet means we have to be as the lowest possible molecular weight of the exhaust gas. So that's the reason why we don't do that. So stoichiometry, I think this is just a simple number of what the number of moles, and the stoichiometric coefficient of oxidizing fuel is in principle the number of moles, but that's obvious because we say that from the Glover reaction, the number of moles is in principle the amount of mass what we have, and that would be the stoichiometric coefficient is in principle the number of moles. And in terms of mass fraction, we have to multiply the stoichiometric coefficient with the mass of the molecule. So I think for you, if you are in rocket engines, we would have the mass fraction 4, meaning the oxidizer to fuel ratio would be 4. This would be stoichiometric. We don't burn stoichiometric in a rocket engine. We have 2 reasons why we are operating fuel rich. The number one is we have a metal wall at 900 Kelvin. If we would have oxygen there, we would burn the combustion chamber wall. So we need more fuel in order to protect our combustion chamber wall. And as I already made the argument with the small molecular weight of the exhaust gases, if we add more fuel, we are basically decomposing the carbon dioxide, and as a product, we get more carbon monoxide than carbon dioxide, and that's a significant reduction of the molecular weight of the exhaust gases, and that raises the performance. So in rocket engine, we are doing better if we throw in more fuel. This gives us a higher efficiency. Now, higher performance in comparison to air engine where we like to be. lean in order to have the best economic performance of the system. In rocket engines, we get the best economic performance if we burn fuel rich. So in terms of hydrogen oxygen, we in principle dilute the combustion process of the product by adding hydrogen, lowering the temperature, but the effect of lowering the molecular mass of the exhaust is more efficient, and that raises the efficiency substantially. So that's an entire different ballgame. This has consequences also in terms of chemokinetic. In aero engines, quite often you could claim that we consume all the fuel. That's not the case in rocket engine. We consume, or we try to consume, all the oxidizer, but we still have under propellant, we have under fuel, and this has to be considered. So if we look into the simple process of hydrogen and oxygen, let's say we have the reactants, we have intermediates such as peroxide. So this is a stable molecule which we generate hydrogen peroxide if we burn hydrogen and oxygen. So that's a classical intermediate. We have also radicals. So hydrogen, radical, oxygen, OH, even HO2. Very important radical, HO2. So there is no direct going from hydrogen to water. So we need those intermediate steps. That's definitely what's happening. And if we look into detail, so N could be any partner who is a collision partner. So this could be any type of molecules or radicals or what is in the particle soup. In hydrogen oxygen, the number is small. In hydrocarbon, the particle soup is tremendous. So it could be whatever, 100, 200, 300 different kinds of species. So each may act as a partner to provide energy through collision to generate radicals. So that's what is basically meant by some M. M is a placeholder for any type of radical or particle which is in a loop. The main thing is that we are able to generate out of that elementary reaction two radicals. Here we generate as well two radicals, and here we generate as well two radicals. So out of the blue, we are generating a large amount of radicals. And again, out of this, we have one radical colliding with oxygen, we may generate two radicals. And this is the very important thing. If we are able to generate more radicals from the beginning, in each step, we have the kind of avalanche process, and that's the prerequisite that we are able to generate an explosion. The number of radicals which are generated are necessary. If they are very larger than one, we may run into an explosion. If we basically have just, let's say, if we would have just one radical is generating another radical, so this is the flow process. If we are increasing number of radicals, then we are increasing the reaction rate. And sometimes, as I said, this goes into flow. What happened as well is that we have also some kind of an extension where we generate radicals, but we also have the possibility that radicals are combining. That would be some sort of reaction, recombination reaction that we have chain termination. It could be that we have two radicals and we have a colliding partner who is taking energy out of those two, consuming it, and say, no, I'm taking it over, and you become a stable molecule. So that would be what we call a chain termination. So this is in principle, you see that in the entire system of hydrogen oxygen, I've tabled here 19 reactions to try to capture all possible reactions in the system. And they go in both sides, right? So that's what the two that arrows are showing. So in both reactions. Early combustion model, I recall some kind of early steps that maybe 30 years ago, people were doing some kind of modeling of hydrogen oxygen, and then they were claiming I'm getting 4,500 Kelvin. And the reason is they were just looking into one direction, so they didn't get this sort of back reaction taking into account, and then they were missing half of the processing, and that gave us these kind of unrealistic magic. So you should be aware that the mechanism you are using takes into account always forwards as well as backward reaction. The reason why this is important is, if you recall what I was mentioning, that we have in a rocket engine in the boundary layer, we are lowering the temperature because we have to cool the water. Meaning that since we change the temperature, if we go nearer to the combustion, to the wall, we change the local conditions. So we may have different kind of reactions. So for instance, there could be some sort of recombination. At high temperatures, we may be able to split up hydrogen into a hydrogen molecule and an OH molecule. But if we are reducing temperature, we shift the chemical equilibrium, and we are recombining those two radicals, meaning that we are generating heat. Meaning, due to cooling in the recombination reaction, we are adding energy into the boundary layer. That's one of the reasons why some of the K omega turbulence models do not work properly in rocket engines, because they don't take into account the local heat release by the cooling process. In aero engines, as I said, temperatures are still high enough that the amount of recombination reactions is small, so heat transfer to the combustion chamber wall should be okay. Maybe 3, 4, 5% difference, and most of the combustion models are already in the range of plus minus 5 or 6%. In rocket engines, you might see 10 or 15 or 20%, and that would be the killer. We don't have that research anymore. So that's one of the reasons why you need to take into account finite rate chemical kinetics, and also make sure that your chemistry model you have in is also having that backward reaction. I'm showing here the, let's say, the hydrogen-oxygen reaction, and this is also important for methane oxygen. We have this kind of behavior that in some of the condition, if you look here, we get explosion for different kind of pressure and temperature. So we may be stable, have a stable reaction without an explosion at higher pressure, but if we lower at the same temperature, we lower the pressure, we get an explosion. The same holds if we go to higher temperature, to higher pressure. We have also the possibility to get an explosion in the system methane oxygen and even methane air. I guess there's a couple of incidents in coal mines where typically they do some drilling, and then there is some exposure of local bubbles of methane inside the soil, filling the tunnel with mixture of methane and oxygen, and in case of ignition, we have an explosion inside the bomb. So we need to also have a mechanism which takes into account when would an explosion occur in methane, oxygen, or methane. So this could be important for people thinking of, they know we can do that also. Just be careful. You know? Make sure that you don't get some unexpected results. So the reason is we in principle have a different kind of, if we look again on the elementary reactions, the reaction path, what we have there, depending on the temperature, so it's responsible to initiate an explosion. So it's the reaction path, the elementary reactions, which are important for the result of each reaction. It's all is in a Vulcan engine, which has roughly 300 kilograms per second of propellant hydrogen. At 120 bar, we want to have strong chemical reaction. E3D is something in the order of the nuclear power plant, so maybe 3.5 gigawatts. Nicely packed. So the mass chain of the diameter is 0.5 meter times 0.5 meter, so this is about the one. And there we have nuclear so that's the reason the explosion really looks way better than any time you could. So, for you, because if we talk about light hydrocarbon in case of methane, in principle, what we need to generate is generating carbon monoxide. That's the first step of the chemical reaction, and then going into further oxidation of carbon monoxide into carbon dioxide. So RH stands for any type of hydrocarbon chain with a molecule that generates the CH3 plus some remaining molecule in the system. And that's in principle what we call small chemistry. So you see that the number of carbon atoms is 1. If you have the small chemistry right, your overall result can't be that low. And the reason is, typically in combustion processes, we have sufficient high temperatures that even thermally large molecules are not stable. So they're breaking down because of the compressors from coming from all sides, cracking reactions. We kill those into smaller units. We even have combustion models which say we have some stochastic modeling of the larger molecules, what we need to have, the small chemistry, that has to be right, then we're doing a good job. And that's the reason why most of them is in principle having one atom, one carbon atom, maybe sometimes 2 carbon atoms. That's the most what we use in most of the methane oxygen models. Then we get 1, 2, more sophisticated one use maybe a couple of 3 carbon molecules with 3 carbon, but most of them are using 1 or 2. With that elementary reaction, the reaction constants are properly, the rate constants are proper, then you should be able to do a good check. So what we have is in principle the handling of the carbon atom. That would be one way, and the other one would be to go from the hydrogen into water molecule. So this is what we do in hydrocarbon combustion. How do we handle the carbon? Of course, we have some smaller, some longer hydrocarbon, but we kill them very quickly into small pieces. And in principle, means we split what is the carbon path with oxygen and the hydrogen path with oxygen. That we generate carbon monoxide and carbon dioxide and water. So that's the overall logic. What we do in the thing that we, even if we have larger molecules, hydrocarbon molecules, killing them by a large number of collision partners into smaller components. And we have the small chemistry, which is in principle generating carbon monoxide, carbon dioxide, and OH, and then OH2. So this could be, for instance, how sort of chemical mechanism looks like. That you have the species, here we would have hydrogen, carbon, oxygen, and nitrogen, and then different kind of species, even COH, O3, CH3, HCO. So this is some kind of different kind of hydrocarbon. So these are species which are known to be important for a certain type of reaction. And then you have a reduced chemical mechanism where you have the reactions, the reaction rates, and these are some kind of constants. And sometimes you see that this is a book, this is from different kind of sources where the rate constants you deduce. If you look, for instance, in fluid different kind of chemistry models, in this, for instance, you will find this way of having the rate constant. And typically you have this sort of production rate or consumption rate of species. That's in principle sort of a source term or a sink term, depending if you formulate it for a fuel or a reaction or a product.
So,
yeah.
If you can, how many of those rate constants are documented when understood? Because one comments as gas. It's a yes.
Oh, sometimes yes. So let's say mechanism, chemical mechanism generation is, I would say, still a gray magic. The rate constants, you might find them, for instance, plus 13, plus 16. For another mechanism, they could say, no, this is plus 14 or maybe 15. So 1 or 2 orders of magnitude, that's big. And the reason is people do some experiments. For instance, in a shock tube, they have, and then they measure a certain reaction by sort of trying to measure when is the heat release, or do I see a chemical reaction? So the shock tube, you locally have the shock wave going through, you heat it up, and then they measure particularly the first OH radical. And then they see, okay, there is it. Now they see what is the concentration rate of a agent by this rate, so that this is a sort of reaction rate. Now the question is, how good is their camera, the TCP camera? Is there some delay in the reaction time? Then, depending on the experiment, if the shock wave is too large in the image, and if they have a boundary layer, and this is impacting the rate. If it's too small, then it's also not right because the propagation speed of the shock wave is not proper. So even the experiment plus minus 10, 20, or 30%, sometimes they're even less. And then the people claim and say, we make a mechanism, and then sort of fitting the mechanism, the constant that they follow our experimental results. Okay, then you have a mechanism which is good for this experiment, but only for this experiment. If you look for a different group with the same experiment, but using a different technique, like a rapid compression engine, you create a different mechanism. Oh, yeah. So you shouldn't be surprised. Yeah. So I just have, so GRI, Aramco, so they have, for instance, this detailed mechanism. So you have it from this until from, let's say, no carbon to butane. They said we need almost 500 species and then 5,000 reactions. So nobody is able to predict that. So you need to boil that down to something which can be handled. And then you get some reduced chemical mechanisms. So there are different kind of what you see. Irreversible reaction. Maybe, maybe not. So laminar flame speed. We've done together with Dr. Slavinsky development, and we were using different kind of experiments from different groups. We're using different kind of mechanisms, different initial temperatures, different mixture ratios. So we have, in principle, developing the reduced mechanism for methane oxygen based on maybe 50, 60 different sets of experiments. And we were not happy with our result, and then we said, okay, we have to sort of quantify the experimental data and say this is a rapid compression engine. I assume this can't be really good because if you move the piston, you initiate also some kind of flow. The flow may impact the flame propagation and the mixing locally. So this is an early experiment, but it has a larger error than a well-defined shock-proof experiment or some plug flow reactor. So we do some kind of uncertainty assessment of the experiment. We say this will trend, maybe we don't believe the data point 100%, but maybe 70-80%. If we do this kind of optimization with uncertainty quantifications, our mechanism is doing better. So don't believe one mechanism. It's just quite often a result of an optimization that the group who is doing the experiment says we have a mechanism which is very good for our experiment. But it's tuned to that experiment. Very seldom you have mechanisms shown saying we have used 20, 50 different sets of data, and that's it. It's not perfect, but obviously now the question is the experimental data set perfect or is the mechanism perfect? It's up to you. So it's the best. So you have to do an educated guess by picking the proper mechanism. Okay, that's what I would want to convey to you today. That there's a lot of information out in the literature, but as I said, the mechanisms are typically in the old times have been developed by people doing the experiments, and they have a tendency to believe their experiment is very good, and then the mechanism is tuned to the experiment. We have done some kind of mechanism development for the last, I think, almost 20 years by now, where we initially started with our methane oxygen mechanism. Let's say we wanted to tune it first and say we are only interested in the ignition process, meaning that if we do ignition under vacuum conditions, so that should be a couple of hundred millibar in the combustion chamber, and we want to ignite oxygen methane. So that was our first optimization goal. And then we said, okay, we want to have some opposite engine, so maybe 30, 50 bar, that's about it. For Vinci, this is 60 bar. So we would like to have not only the ignition, but also the steady state operation at high pressure, moderate pressure. That was the next step of keeping the ignition there, because in principle, since we inject our reactants with liquid oxygen, so it has to vaporize and it's cold, and also the methane is coming cold, so we have some low temperature. So the ignition process should still work even at higher pressure, because we go through the ignition first and then we go through the step of chemical reaction. So that's the reason why we kept the ignition mechanism for the small chemistry, and then step by step checking also into higher pressure. And now I think we are at 1. Now, do you have questions? I think it's interesting because I like that you are interested in chemistry, in combustion. Although people think we don't do that anymore, but I think the last carbon atom will be burned in an aero engine, and I think the people would maybe in 40, 50 years would say, where did we get carbon dioxide and reuse it in making a fuel out of it by adding hydrogen to it and then burning methane into our it's that's the best way of propelling, because in electric, I cannot imagine that we have we go transatlantic with electric, even with hydrogen liquid. No idea why people would burn hydrogen. I could imagine that we use hydrogen in a fuel cell. Maybe so the efficiency is 90%. Burning, that French guy, Mr. Carnot, said, oh, you can't be better than really something, right? So why do the combustion process if you could do better in a fuel cell? So burning hydrogen in my gas turbine. That's what, even if it's very cheap, it's efficient. And cheapest. Hydrogen is not cheap. Not yet. So I guess that would be. Okay. Question? No?
I have a question about modeling. When you, like you said, there are obviously different combustion models out there. How or how can you be confident that the model you're using is accurate, or rather accurately painting a picture of what's actually
Out of the blue, I think you are correct. So I think you need to do some exercise and experience to check and test. For instance, what normally people would claim if they would predict what's going on in the boundary layer, people would say that omega SVT is the best you can get. Right? I mentioned that's good for fluid mechanics. It's even good for having boundary layers in there, just because of the it's a small recombination reaction in an organism. We have, due to the large delta T of elements, and the fuel rich, we are changing the composition. So we change the species concentration, we generate heat, species with different kind of heat capacity as well as thermal conductivity. So the boundary condition will be anti-different when it comes to heat load to the combustion chamber wall. If it comes to, let's say, the overall performance, you don't care. Metering is easy. However, if it comes to heat load and heat load, you are in trouble. So typically what people now do is some kind of wall function and any viscosity. Called variance of viscosity. So still some runs averaging, not everybody is using it, but it's still but specified and we do our here. So that's just the patient concept. I think Swedish.
yeah, it was just how much. Is it that people are just they look through a lot of studies and then to themselves, okay, this is the best one to use, or what do they typically do in the industry?
Let's say the Ariane guys have their own code. They do a flamelit approach, but very sophisticated flamelit code. It's non-adaptive flamelets. and they try to analyze the boundary layer. And based on defining locally adaptive numbers, you know what adaptive is? It's principle from, let's say, chemical kinetics or chemical engineering. People try to have locally what is the time scale of the chemical reaction and relates it to the time scale of return. And they see, for instance, from a computational point of view, you have a sort of residence time of the mixture inside the computational cell. The residence time is smaller than the time to reach the chemical equilibrium. So you cannot assume that you have a chemical equilibrium, meaning the classical flame rate approach is not working. So in order to be able to do that, what they do is try to find out what is the local doctor number in that computational cell. And that means they have the reduced chemical mechanism. They try to identify what is the characteristic time out of 50 reactions. So select those which they feel based on the sensitivity analysis. These are the most important reactions. Out of that, they predict a time scale, and then they relate it to what is the local fluid time scale in the system. Then they say, okay, I have a Dampfkühler number. If it's near 1, meaning that fluid and chemistry playing the same league, they need to take into account finite rate chemical kinetics. If the Dampfkühler number meaning is very high, then the chemical equilibrium properly. And then they need to take into account what happens if temperatures are low, that there is no volcanic reaction. Flamelet would say it doesn't know really about what is the time scale, so it needs to see the equilibrium. So you need to take into account the fact that at a certain temperature limit, there is no volcanic reaction. So you have frozen case. You need to have that new composition and apply for that composition the proper enthalpy. So at the end, typically the normal flamelet would mean that I predict the chemical equilibrium and store it in a library. And this would mean we have a mixture fraction, the variant of the mixture fraction, and so 4-dimensional. In non-equilibrium of this, they would have a 6-dimensional library to be more predictable. So you can do that. Flamelet also quite often use some kind of progress variable in order to take into account local progress in terms of how fast is the reaction progressing, in terms of having some kind of event. So there is some kind of workaround for cases where classical flamelet equilibrium doesn't work. But
that's a bit much.
Yes, but you have to take into account that we have not only just that global reactions, but a large number of elemental reactions, and each depends on species concentration, temperature, and pressure. Plus, what is not taken into that models, we say that M, the collision partner. Now, each collision partner may have a different kind of electrochemical interaction potential, so it may be more or less effective in locally generating a kicking of the chemical reaction. This is not yet in all those mechanisms. And what they don't have as well is excited state molecules. So non-equilibrium. We did, for instance, one kind of measurement where we try to measure temperatures with a laser-based system called coherent anti-Raman slope scattering mechanism. So you have one laser photon at a certain wavelength, meaning color. You type the molecule, raise it into a certain position that it accepts another color. So it goes up, keeps that energy for maybe a couple of 150 seconds, and then it realizes that I can keep that. Then it emits the energy, it falls down, and the energy is basically emitted in a certain direction with a certain color, and out of the color and the intensity of the emission, you can get what is the local concentration of those species as well as what is it. Now, we assume that we are using rotational, let's say the rotational behavior. So we have different kinds of, we reach the freedom of molecule. And what we find out at the same place, we are measuring two different species, hydrogen and water. And in the reaction phase, the water was colder than the hydrogen. We say, right, the water is just separated, it has to be hot. Now we did some analysis, so with some quantum dynamic predictions, and then found out, the molecule is not in thermal equilibrium, so it has not had the time since its generation to distribute all the energy in all the degrees of freedom. We can measure 1 degree of freedom, it's maybe high, but the overall temperature will be still low, so that you may have a plasma, but it's cold. So it's locally, it's 1 degree of freedom that has temperature, but the overall temperature is not yet there. And nobody is having these kind of mechanisms. And exciting stuff. And again, what's still happening? This is a great magic because it's a lot of different. Okay, further question. Yeah. But never.
Yeah.
Yeah. Really. Even with chemistry, no, I'm chemically really good at this. They ended up doing a lot of different things, including diagnostics, hydrogen technology, and then I moved into operating. Really, explosion, very low temperature, all equilibriums. We don't do that in the quick channel, but there is something to do with methane. It could be that, you know, about core methane, but normally some liquid by natural gas. You may be in a supercritical stage, and now you have energy in the cooling channel, you heat it up. And what may be in a certain mixture, that instead of having, since you are already supercritical in a gas, one component may condense. So you get a two-phase flow by adding energy to the system, and the supercritical will always exist. So this is, if you look at a book called Retrograde phase change. So retrograde means unexpected phase change. That's something. I would say so. So it's something that makes it's really interesting to look in more detail. Because as an engineer, we have to do things that make sense. But we are no managers. We are not working at administration. We do the real stuff. Okay, then see you next week. Thanks for your attention.